In the first kinetics lesson, we discussed the collision theory and how different factors can affect the rate of the reaction. We looked at how temperature affects the rate of the reaction and used the Maxwell-Boltzmann distribution diagram in order to explain that factor. We looked at how the activation energy of a reaction can affect the rate, and we looked at potential energy diagrams in order to explain that. What we didn't look into with any great detail was how the concentrations of reactants will affect the rate of the reaction. We need to study this in more detail by presenting the rate law. The rate law of a reaction is going to give the relationship between the rate of the reaction and the concentrations of the reactants. We know that the rate is proportional to the concentration of the reactants in a reaction. So for example, in this reaction, A plus B going to some products, we know that the rate is going to be proportional to the concentrations of A and B. We know that it's proportional, so if we want to change that into an equation, we need to introduce a constant. And the constant that we're going to use in our rate law is lowercase k. It's called the rate constant. So this equation that we have right now shows us that the rate is dependent on the concentration of the reactants. Now what you'll notice is that there are powers that the concentrations are raised to. And this is what we are going to be looking into in more detail. How much a particular substance affects the rate of the reaction and how it affects the rate of the reaction must be determined experimentally. And it's not dependent on the coefficient in the balanced chemical equation. And we must use experimental data in order to determine the powers of the concentrations in the rate law. So let's look at an example. This reaction here has this experimentally determined rate law. So the rate is equal to a rate constant times the concentration of H2SCO3 raised to the 1, I minus raised to the 3, H plus raised to the 2. You'll notice that the coefficients in the balanced chemical equation do not match the powers in the reaction. These powers are determined by experiment, and you'll see the experiments that are done in order to determine them. These numbers are called the order of the reactant. So this particular reaction is first order in H2SCO3. It is third order in I minus, and it is second order in H plus. The overall order of the reaction is the sum of all of the exponents. So in this case, the overall order of the reaction is 6. Now, the meaning of the exponents is going to become more clear as we move through the lesson. For now, we're going to look at the experimental data that's collected and how we can use it to determine the order of a particular reactant in a reaction. In order to determine the exponents in the rate law, what we need to do is we need to change the concentration of a particular reactant, and we need to monitor what happens to the rate. So for this particular reaction, if we want to study it, we've got one reactant. So an experiment that would be done to determine the rate law would be one where we change the concentration of the N2O5 and look at what happens to the rate. So this is the table in your notes, and you can see what happened to the rate. So in this case, we halved the concentration, and the rate was also halved. Okay, so we need to look at the relationship between the concentration and the rate. We know that the rate in general is equal to K times the concentration of N2O5 raised to some power. So what we're trying to determine with this data is what the exponent is. And in this case, if we halved the rate, okay, when the concentration was halved, we can see that in order for this expression to be true, the exponent needs to be equal to 1. The rate constant here is a constant. Okay, so we're looking at the connection between the concentration, the exponent, and the rate. So the rate law for this particular reaction is the rate is equal to the rate constant times the concentration of N2O5 to the 1. So for this particular reaction, it is first order in N2O5. Okay, let's look at another example here. In this example, we're looking at this reaction here. So NH4 plus NO2 minus goes to N2 plus 2H2O. The experimental data that we've collected is here. Now in this case, we're looking at a scenario where we've got two reactants. So we know that the rate is going to be equal to the rate constant times the concentration of NH4 plus raised to some power times the concentration of NO2 minus raised to some power. The exponents of the reactants each need to be determined experimentally and separately from one another. So in order to set up an experiment, what we need to do is we need to change the concentration of one reactant at a time and look at the impact on the rate of the reaction. So let's look at comparing trial 1 to trial 2. The concentration of the NH4 plus has been maintained. But during that time, what has happened is the concentration of the NO2 minus has been doubled. So by examining trial 1 to 2, we're going to be able to see what the exponent of NO2 minus is in the rate law by looking at what happened to the rate of the reaction. In this case, the rate of the reaction when we doubled the concentration of NO2 minus is also doubled. If you're not sure, what you can do is just divide, take the 2.7 times 10 to the negative 7 and divide by 1.35 times 10 to the negative 7, and you'll see that it's double. So the constants in this situation are the K and the NH4 plus. I haven't changed the concentration. So I know the change in the rate by doubling the rate has come from doubling the concentration. So we can take a moment and look at what that means for the exponent. In that case, the exponent needs to be equal to 1. Okay, so we know the exponent n is equal to 1. To look at the impact that the concentration of NH4 plus has on the rate, we need to compare a scenario where the concentration of NO2 is being held constant. So if we compare trial 2 to trial 3, you can see that the concentration of the NH4 plus has been doubled and the rate of the reaction is also doubled. As we saw from our previous example, when the rate is doubled with the doubling of the concentration, that means that the exponent must be 1. So for this particular rate law, both the exponents are equal to 1. So the formal rate law is NH4 plus times NO2 minus. Now, what we can also do is determine what the rate constant is. And so if we look back to here, If we want to determine what the rate constant is, we've got the rate law, we know what the exponents are, and we've got an equation. So if we want to figure out what the constant K is for this particular reaction, what we need to do is take one of our sets of data. So in this case, if we take our data from trial 1, and we need to sub that into the rate law. So we know the rate, we know the concentration of NH4+, we know the concentration of NO2-. We can simply rearrange this equation in order to solve for K, the rate constant. And the rate constant here is 2.7 times 10 to the negative 4. Okay, I'll talk in a moment about how to determine the units for this. So if we want to know the units for the rate constant, and it's important to determine these because they do give us information about the reaction, to look at what we have. So rate is equal to the rate constant times the concentration of various reactants and products. The units for rate are mole per liter per second, so mole per liter second. The units for concentration are mole per liter. So in this case, in the example that we had, if both of the concentrations are first order in the rate law, this is going to be mole per liter, this is going to be mole per liter. So when we look at this, if we want to rearrange to find the units for the rate constant, we've got mole per liter per second, and we're going to bring the liter squared over and the mole squared over. Okay, so the units for K are going to be liter per mole second. Now this is for a second order reaction. Okay, if I change this, so say it becomes a third order reaction and this is squared, this is going to be squared. So what's going to happen is this is going to be cubed and this is going to be cubed, and I'm going to be left with squared and squared. If this was a fourth order reaction, so a 2 and a 2 or a 1 and a 3, then what's going to happen is this is going to be a 4, so I'm going to have a 3 and a 2. Okay, so if you look, if you've got a first order, second order, third order, the units, you could work it out for each one. The units for a first order reaction are 1 over S. For a second order reaction, are liters per mole second. For a third order reaction, are liters squared per mole second. For a fourth order reaction, are liters cubed mole cubed per second. Okay, so if you can see the pattern here, in general, the units for the rate constant are liters to the n minus 1 over mole to the n minus 1 per second, where n is equal to the overall order of the reaction. Now, this is important because it's expected that if you're given the units of the rate constant for a particular reaction, you should be able to state the order of the reaction. That's why we need to review this. So what that also means is that when you're given data from a reaction and you're asked to find the rate constant, you need to include the units for the rate constant. You can either use the general formula for the units, or you can set it up and just solve algebraically to figure out what the units are. Okay. Now, there's another example in the notes for you to do, okay, where you've got three different reactants. So you need to determine the exponents on all three reactants, and then you also need to determine the rate constant with the appropriate units. So it'd be a good idea for you to stop the video at this stage and actually try that question before moving on. Now what we're going to do is skip ahead in your notes. Okay, the next few pages are focused on some experimental determinations of rate law, which we are going to do, but what we're going to do in this lesson instead is apply the rate law to the mechanism. Okay, so you can skip ahead in your notes to the section that's entitled Reaction Mechanisms, and I believe that starts on page 38 in your notes. Now, in previous stages of the course, we've talked about reaction mechanisms, especially in organic chemistry. And when we think about reaction mechanisms, the reason they're important is because, as we know, in order for a reaction to occur, collisions need to happen. But when you think about some of the reactions that we studied before, so even the first one in this mechanism discussion that had one molecule of H2SeO3 with 6 molecules of I minus and 4 molecules of H plus. When we think about that reaction occurring, it would be next to impossible for the reaction to occur with one single collision, because that would involve one molecule finding 6 molecules of iodine and 4 molecules of H plus or ions of H plus all simultaneously. Okay, so when you think about it that way, it seems to make sense that reactions don't often occur in one step, but they occur in elementary steps. And this series of elementary steps that lead to a product formation are called the reaction mechanism. I used to live in Toronto, and so when I lived in Toronto and I would go home to Ottawa, I would break up the drive in steps. So I could think about it as one full journey going from Toronto to Ottawa, or I could think about it in different steps. Okay, so this is a good kind of visual of what a mechanism is, example of that. So from Toronto, I would go from Toronto to the lakeshore, and then I would go from the lakeshore to the DVP, and then I would go from the DVP to the 401, and then the 401 to the 416, and the 416 to home. Okay, these, the lakeshore, the DVP, the 401, the 416, these are what are called intermediates. Okay, so they're not part of the overall journey. The overall journey is going from Toronto to Ottawa. And when we add up all of these elementary steps, that's what we see is the overall journey. So we've done a lot of adding up of reactions in this course. And this is another case where we can add up the elementary steps to get the overall reaction. Here's another example. When we've got 2NO plus O2 going to 2NO2. This reaction doesn't happen in one step. So it doesn't occur by 2 molecules of NO colliding with 1 molecule of oxygen to produce 2NO2. It happens in elementary steps. And the elementary steps that occur are these ones. So first of all, the 2 NO molecules collide to produce N2O2. Then this N2O2 intermediate reacts with oxygen to produce the 2NO2. So these are elementary steps, and this is the overall reaction. In this case, the N2O2 is what is called an intermediate. And an intermediate is something that appears as part of the mechanism, but doesn't appear in the overall reaction. So it's produced in one step of the mechanism and then it's consumed in a later step. And these intermediates are often very unstable on their own and thus very reactive. When we look at a mechanism, we can talk about the molecularity of a particular step. And so the molecularity is just really how many molecules are involved in that particular step. So let's look back at this particular mechanism. In this reaction, the molecularity of this step is 2 because there are 2 molecules that are involved. As in this one, it is also 2 because there are 2 molecules involved. Okay, the molecularity of this overall reaction is 3. So you can see how the intermediate or elementary steps rather have fewer molecules involved. Now, what we want to do is make a connection between the rate law and the mechanism, because the rate law actually gives us an indication of what is occurring in the mechanism or what intermediate steps must be occurring in the mechanism. So this is the primary reason why chemists study or want to determine the rate law of a reaction. It's ultimately because they want to know what the mechanism of a reaction is. The more a chemist knows about the mechanism of a reaction and how specifically a reaction is carried out, the more they can make changes to how they perform an experiment or how they do a reaction in order to get an optimum amount of product or a pure product or a particular product that they're looking for. So understanding the mechanism of reaction is really, really important. So we're going to study the rates to make a rate law, and that's ultimately going to help us to postulate a reasonable reaction mechanism. So the connection is to the rate law. Okay, the rate law gives us information about what is called the slow step or the rate determining step of a reaction. Let's look at this example. In this example, we've got a reaction where 2NO2Cl reacts to form 2NO2 and Cl2. In studying this reaction, it was determined that the rate law is rate is equal to K times NO2Cl, and it's first order in NO2Cl. So what this means is that they could use this information to propose this mechanism. This rate law is telling us that there is a step in the mechanism that involves one molecule of NO2Cl. And that particular elementary step in the mechanism is actually controlling the rate of the reaction. So knowing that there was a step that involved one molecule of NO2Cl, the following mechanism was proposed. They decided that rather than 2 molecules of NO2Cl colliding, that this would be realistic. One molecule of NO2Cl decomposes to form NO2 and Cl. This Cl is now a very reactive intermediate, and it reacts with a second NO2Cl molecule to produce NO2 and Cl2. So this is the proposed mechanism. From this information, we now can look back at our rate law and decide which of these steps is our rate determining step or our slow step. It's the one that's basically controlling the overall speed of the reaction. Because the rate law involves one molecule of NO2Cl, we know that this first step is likely the slow step in the reaction. It's the one that's controlling the rate of the reaction. It also makes sense because this chlorine is likely, as an atom, it's an intermediate and it's going to be very reactive. Okay, so not only do we have this proposed mechanism, but we can say that the first step is likely the slow step in this mechanism and the second step is fast. Let's look at another example. We've got a reaction of 2NO plus 2H2 going to N2 and 2H2O. After some study, the mechanism was determined to occur in the following two steps. 2NO plus H2 going to N2O and H2O, followed by N2O plus H2 going to N2 plus H2O. So from this information, it's asking us to produce the overall rate law based on the mechanism. And what we know is that the slow step in a mechanism is connected to the rate law of the reaction. And it actually gives us the molecularity and the exponents of our rate law. So our slow step involves 2 molecules of NO reacting with 1 molecule of H2. So what that means is that the rate law is rate is equal to K times the concentration of NO squared times the concentration of H2. Okay, so you can see the connection between the stoichiometry of the slow step of the mechanism and the rate law, which is not the same as the stoichiometry in the overall reaction. So it's really important to distinguish between the two. The rate law is connected to the slow step of the mechanism. So let's look at another example here. We've got a decomposition of hydrogen peroxide. It is facilitated by iodide ions. It gives us the overall reaction. The little phrase there, facilitated by iodide ions, that's giving us an indication that there's a catalyst in this reaction, which we'll see and investigate in the mechanism. So the experiment is completed and the rate law is found to be rate is equal to K times the concentration of H2O2 times the concentration of iodide ions raised to the 1. So this particular reaction is first order in both H2O2 and I minus. And if we look at the mechanism of this reaction that's been proposed, okay, we can see the connection here. So we know that the rate determining step of this reaction is going to involve 1 molecule of H2O2 and an iodine ion, okay, which we see in step 1 of the reaction. H2O2 plus I minus goes to H2O plus IO minus, and then in the second step, another molecule of H2O2 reacts with this IO minus intermediate. The molecularity of each step of the reaction is 2. So that simply means that 2 molecules need to collide, okay, in each step of the mechanism. The step that's the rate determining step in the reaction is the one that's connected to the rate law. So it involves 1 molecule of H2O2 and an iodine ion, which is step 1 of the reaction. The substance that's acting as a catalyst in this reaction is the I minus. And we know that it is a catalyst because a catalyst is something that's used in the reaction, okay, and we know that it affects the rate. And it's not consumed in the reaction. So the I minus is used in step 1, but then reproduced in step 2, okay, which is the opposite of an intermediate. So an intermediate is something that is produced in one step of the reaction and then used up in another step of the reaction. So in this case, The intermediate is IO3 minus. Okay. When we're looking at an energy profile, we're starting with H2O2. We're going to make I minus, okay, and then we're going to do the second step of the reaction. When you want to show an energy profile, we have very little information here. Like, we don't know if it's an exothermic or endothermic reaction. But what you do know is that the activation energy of the second step is going to be smaller than the activation energy of the first step. Okay, so that's about all you have to go by. Okay, but each individual reaction is going to have its own activation energy. The last thing that we're going to discuss is catalysts and the terminology that we use to explain the effect of catalysts on the rate of the reaction. I'm skipping ahead again. I'm going to go over the Arrhenius equation in the final video. I'm skipping ahead to page 46 in your notes. So catalysts and activation energy. Now, as we've discussed, a catalyst is something that is used to speed up a reaction, but it doesn't change during the chemical reaction. So it makes a catalyst something that's reusable. We can have either a homogeneous catalyst or a heterogeneous catalyst, and that simply means that the catalyst can either be in the same phase as the reaction or different. So if you have a solution and you put a catalyst like an acid into the solution and it's also a solution, then that's a homogeneous catalyst. If you've got something where the reaction is taking place in solution, but you add some kind of a solid that's acting as a catalyst, that would be a heterogeneous catalyst. Now, in order to increase the rate of the reaction, one thing that we can do is if we've got a larger number of molecules with enough activation energy, then we're going to be able to overcome that activation barrier and produce products. Now, what's happening when we add a catalyst is we are providing an alternative mechanism for the reaction. So you can have a mechanism with a catalyst or without a catalyst. And usually what the catalyst will do is provide a pathway that has a lower activation energy. Okay, so in this particular example, the reaction without the catalyst has a high activation energy, but by adding the catalyst, there's an alternative pathway with a lower activation energy. If we connect this to the Maxwell-Boltzmann diagram, okay, you'll remember we had just at a normal temperature, we had an activation energy. And we said that any molecules beyond that point had enough energy on their own to overcome the activation barrier. By adding a catalyst and providing an alternative pathway, what we've done is we've got a lower activation energy for the reaction to take. So therefore, all of a sudden, we've got more molecules with enough activation energy, enough energy to overcome the activation barrier of the reaction. So that's the correct way of explaining that a catalyst can increase the rate of the reaction. It is incorrect to say that the catalyst lowers the activation energy of the reaction, because it doesn't actually change the activation energy of the particular reaction. It's simply providing an alternative path. So for example, if you look at this reaction, making sulfuric acid out of sulfur and oxygen could occur in this three-step process. Okay, so you can take a minute and examine that three-step process. By adding a catalyst of NO2 to this system, what happens is this second step, which is likely a slow rate determining step for this reaction, can be made quicker. And the pathway that it takes, rather than this pathway of SO2 molecules reacting with oxygen directly to form SO3, is this step. Okay, so the SO2 reacts with some NO2. This will have a lower activation energy likely. And then the NO, this reactive intermediate, reacts with oxygen to produce the SO2, the NO2. Okay, and overall, what's happening here is the SO2 is converting to SO3. Okay, it doesn't look like much of a change, but what we can say is that this catalyzed reaction has a lower activation energy, so it's going to happen quicker than this one that's given up here. Okay, so a catalyst can simply change the pathway of the reaction and make it go faster in that way.